Cement is one of the most widely used materials on Earth, the backbone of modern civilization, holding together highways, skyscrapers, bridges, dams, tunnels, and entire cities. Yet very few people ever see how this dull gray powder is actually made. Behind every bag of cement is a giant industrial operation involving quarry blasting, rock crushers the size of houses, precision-controlled kilns hotter than volcanoes, grinding mills loaded with steel balls, and automated packing lines that fill bags by the thousands. And today on the How Factory, we're going deep inside those massive cement plants to show how raw stone is mined, crushed, blended, heated, ground, and packed into the fine powder that powers the global construction industry. What looks simple at the store is the outcome of one of the most energy-intensive and precisely engineered processes in heavy manufacturing. The journey begins at the quarry, the source of limestone, the primary raw material for cement. Quarries are enormous open-pit mines carved into hillsides where drilling rigs bore deep holes into solid rock. These holes are filled with carefully calculated explosive charges. Blasting crews detonate entire rock faces at once, sending thousands of tons of limestone crashing to the quarry floor. The blast pattern is engineered to produce fragments of a specific size that feed efficiently into crushers, reducing fuel consumption and increasing mill productivity. Bulldozers and loaders push the rubble into piles where huge haul trucks, some capable of carrying over 100 tons at a time, deliver the limestone to the plant's primary crusher. The crusher is the first transformation stage and one of the most dramatic. Giant rotating jaws or hammer mills smash the limestone boulders into pieces only a few inches across. Dust collectors and spray systems control airborne dust, while magnets remove stray metal from the blasted rock. From here, the crushed limestone travels on long belt conveyors, sometimes several kilometers, directly into the plant. Meanwhile, clay, shale, iron ore, or sand is also mined or delivered to the plant, because cement requires a precise chemical blend of calcium, silica, alumina, and iron. These secondary materials are crushed and stored separately in covered stockpiles. Next comes raw mix preparation, the stage where multiple raw materials are blended into a perfectly balanced chemical recipe. The crushed materials feed into proportioning systems controlled by computer algorithms. Each conveyor is equipped with weigh feeders that measure mass flow in real time. The plant's control room uses chemical models to adjust feeder rates so the mixture entering the grinding mill maintains the ideal ratio. A typical raw mix might include 80% limestone blended with precise quantities of clay and iron-bearing minerals. Consistency is critical. Even a small variation can destabilize the kiln and reduce cement quality. The raw materials then enter the raw mill. Many plants use vertical roller mills, towering machines with rotating tables and heavy steel rollers that crush the mixture into fine powder known as raw meal. Others use ball mills, massive rotating cylinders filled with thousands of steel balls that pulverize the minerals through cascading impacts. Hot exhaust gases from the kiln are used to dry the raw materials as they grind. The raw meal leaving the mill is so fine it resembles flour, and it's transported pneumatically to blending silos the size of small office buildings. Inside these silos, air pads or mechanical mixing systems homogenize the powder into a perfectly uniform feed for the kiln. Now the most critical and energy-intensive stage begins: clinker production in the rotary kiln. The raw meal is preheated in a tower of cyclone separators where hot kiln gases swirl through the falling powder, heating it to around 800 degrees Celsius before it enters the kiln itself. These preheaters dramatically reduce fuel consumption by capturing waste heat. At the base of the preheater tower, a precalciner injects fuel: coal, natural gas, waste oil, or alternative fuels like shredded tires or biomass, to drive the chemical decomposition of limestone into lime. This alone consumes nearly 2/3 of the kiln's total energy. Once precalcined, the material enters the rotary kiln, a giant steel cylinder that may stretch over 60 meters long and rotate slowly on massive support rollers. Inside, temperatures reach 1,450 degrees Celsius, hotter than the molten lava inside volcanoes. At these temperatures, the raw materials melt partially and fuse into marble-sized nodules called clinker. This physical and chemical transformation is the heart of cement manufacturing. The kiln must maintain extreme precision. Too hot and the clinker overmelts. Too cool and it forms weak, dusty material. Operators watch flame cameras, temperature sensors, gas analyzers, and feed rates from a control room resembling an air traffic tower. Burning conditions are adjusted second by second through computerized controls. The glowing red clinker exits the kiln into a clinker cooler which blasts it with forced air. The cooler not only hardens the clinker but recovers heat for reuse in the kiln system. Conveyors carry the cooled clinker to storage silos where it waits for the final transformation, grinding into cement powder. Clinker grinding takes place in gigantic mills similar to the raw mill, but designed to pulverize much harder material. Clinker is fed alongside a small amount of gypsum, a mineral that controls cement's setting time, and sometimes additional materials like fly ash or slag, depending on the type of cement being produced. Inside the cement mill, steel balls or heavy rollers crush the clinker until it becomes a fine gray powder. During this stage, plant operators monitor fineness, temperature, and energy consumption. Overgrinding wastes power. Undergrinding produces weak cement. High-efficiency separators classify the ground meal, sending coarse particles back into the mill while allowing fine cement to pass through to storage. The finished cement is conveyed to huge cement silos, each capable of holding thousands of tons. These silos keep the cement dry and protected from contamination. Aeration systems inside the silos ensure the powder remains fluid and doesn't pack or crust. At this point, the cement is ready for packaging and distribution, but the factory still has several high-speed mechanical stages to go. In the packing hall, one of the busiest parts of the plant, automated bagging machines fill 25 or 50 kilogram paper bags with incredible precision. The cement flows from the silo through feeding spouts controlled by pressure sensors and electronic weighers. The filling system rapidly dispenses cement until the bag reaches its exact target weight. Air is evacuated from the bag so the material compacts properly. Then the bag is sealed with glue or stitching. Modern packing lines can fill more than 4,000 bags per hour. From here, robotic palletizers stack the bags onto pallets with machine-perfect alignment. Stretch wrappers secure each pallet for transport, protecting the cement from moisture during shipping. Not all cement is bagged. A significant portion is sold in bulk and pumped into tanker trucks or rail cars. Large pneumatic loading systems blow dry cement into sealed tanker compartments. These trucks then deliver cement to ready-mix concrete plants where it becomes the backbone of construction projects. Throughout the entire cement-making process, quality control is constant. Laboratories test raw materials, raw meal, clinker, and finished cement for chemical composition, particle size, setting times, strength development, and impurity levels. X-ray fluorescence spectrometers provide instant chemical analysis. Strength samples are cast into test cubes and crushed by hydraulic presses after 1, 7, and 28 days to measure performance. If results drift from specification, operators adjust mill settings, raw mix proportions, or kiln parameters to correct the process. The consistency demanded from cement plants is extraordinary. Every batch of cement must behave predictably at construction sites, where curing time and strength determine structural safety. Environmental systems play a major role as well. Cement plants use advanced air pollution controls such as baghouse filters and electrostatic precipitators to capture dust. Kilns may co-fire alternative fuels to reduce CO2 emissions. Waste heat recovery units capture thermal energy from the kiln and cooler to generate electricity. Water recycling systems minimize fresh water use. All these technologies work together to reduce the environmental impact of one of the world's most essential materials. What makes cement production so remarkable is the combination of geological raw materials, extreme heat, mechanical power, and micron-level precision. Limestone blasted from a quarry becomes molten rock inside a rotating furnace before being crushed into a powder that must behave exactly the same in every bag shipped worldwide. It is heavy industry at its purest. Loud, hot, massive, and unforgiving, yet engineered to operate continuously and reliably at incredible scale. And that is exactly how cement is mined, crushed, blended, burned, cooled, ground, stored, packed, and shipped by the millions of tons. A monumental fusion of mining, chemistry, thermodynamics, and industrial automation hidden behind one of the most essential materials in modern construction. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.